This video is on open and closed sets in metric spaces. So before we define open and closed sets in metric spaces, let's first think about some open and closed sets in the real numbers. So if we're just thinking about the real number line, one type of set we might naturally think of as open is the open interval from A to B, so that does not include its endpoints. That would be our natural kind of thing we might think of as an open set, whereas a closed interval we might think of as the closed interval from A to B, the interval that does include its endpoints. Let's think about some properties of these types of sets. So if we're thinking about an open interval on the real number line, one property it has is that for any x in that interval, in that open interval, there's like a cushion around it that's also a subset of that interval. So there is some epsilon greater than 0 such that the open interval from x minus epsilon to x plus epsilon is a subset of the open interval AB. So if we just pick any x in here, no matter how close to an endpoint it is, there's going to be some tiny little open interval around x that is still a subset of the open interval AB. Whereas closed intervals do not have this property. So for example, if we're talking about the closed interval AB, then A is in the closed interval AB, but there is no epsilon greater than 0 such that x or A minus epsilon, A plus epsilon is a subset of that closed interval AB. Because no matter how small epsilon is, we're going to be just outside of it when we do A minus epsilon, for example. All right, what are some other properties? So this is a property that open intervals have that closed intervals do not have. How about, closed intervals contain their endpoints, obviously, or closed intervals of the real line. So it contains its endpoints, contains A and B. Over here, we don't contain endpoints, so doesn't contain endpoints. And sort of similarly to that, along those lines, is that this also contains all of its limit points. And we're not going to define that very formally for now, but we will be defining that formally in the next two sections. So containing its limit points, like say we have a sequence x sub n that's entirely a subset of some closed interval AB. That means that its limit, the limit as n goes to infinity of xn, will also be an element of this closed interval AB. Again, we're not proving it formally for now, but we'll prove it more generally for closed sets in metric spaces. But that's not true over here, and just as an example of it not being true for an open interval, let's say that we have the open interval from 0 to 1, and let's say that we've got the sequence 1 over n. Then this sequence converges to 0, obviously, as n goes to infinity, and that's not in the open interval from 0 to 1. So this does not contain its limit points. We've also done other things with open and closed sets. A lot of it, say when you're in calc, you might say like, yeah, that's just some weird detail that you might not think about a lot. Like, for example, the extreme value theorem in Calc 1 says that if a function is continuous over a closed interval, then it attains its max and min over that closed interval. Whereas if we're thinking we don't have the extreme value theorem for open intervals, like for example, f of x equals x cubed over the interval, let's say again 0, 1. So that function attains neither its max nor its min over that open interval. Continuity is really defined using open intervals as well. So you may have seen a more formal definition of continuity in the past. If not, we'll see one this chapter, and we'll see it both for metric spaces and for this specific example of functions mapping the real numbers to the real numbers. One other thing to note is that, if we think about, say, the union of two open intervals, A, B, union C, D, then all these properties we have above still hold. And if we think about the closed interval AB union with the closed interval CD, then again, those properties above are still going to hold. If we think about the intersections, same deal. Okay, so here is our definition for, first of all, just an open ball in a metric space. Not quite an open set yet. So let's let XD be a metric space. In other words, X is a set and D is a metric on that set. Let A be an element of the set X, and let R be a real number greater than 0. Then the open ball centered at A with radius R is the set B sub D of AR. The open ball centered at A with radius R is the set of points X in X such that distance between A and X is less than R. And the closed ball centered at A with radius R, similarly, same deal except that it's X in the set X such that the distance between A and X is less than or equal to R. Let's just observe that open intervals and closed intervals are open balls and closed balls respectively in the real number line. So for example, the open interval from 1 to 2, we could think of that as the open ball BD, usual metric, centered at, the center of that is 0.5 and its radius would also be 0.5. And then the closed interval from 5 to 9, well, that would be the closed ball. Now we have square braces to denote closed. The center of that is 7 and it has radius 2. So each of these things are open and closed balls in R with the usual metric. Now I would like you to draw some, in this case, open balls for the usual metric for R squared and the taxicab metric for R squared. Just remember this usual metric is the square root of the subtraction of the x coordinates squared plus the y coordinates squared. Is the distance between 2 points x1, y1 and x2, y2. And the taxicab metric is given by the sum of the differences in the x coordinate and the y coordinate. Okay, so I would like you to draw in the plane this open ball centered at 0, centered at the origin 0, 0 with radius 2 in each of these metrics. So pause, think about that, we'll talk about it together. So for this open ball, we're looking at the distance x between x and 0 being equal to the square root of, since this is x1 minus 0, we've just got x1 squared plus y1 squared, if x1, y1 are the coordinates of the point x, being strictly less than 2. So it's actually easier to think about sort of the endpoints of this open ball, the boundary of it. So one such point on the boundary would be the point 2, 0. That is not in this open ball, but it's kind of just at the boundary of it, because if we do x1 squared, 4, plus 0 squared, that would be square root of 4, which is not actually less than 2, but just on the verge of being less than 2. And similarly, these points 2, 0, sorry, this was 0, 2, sorry about that, 2, 0, 0, negative 2, and negative 2, 0 would also all be on the boundary of this set. What else is going to be on the boundary? So another thing that would be on the boundary would be, say, for example, the square root of 2 comma square root of 2. So that would be a point such that for that x and y squared, that would its square root would be exactly equal to 2. So square root of 2, square root of 2, and similarly all the negative versions of that, negative and positive versions of that. And in fact, if you take a look at this, this is really the definition of a circle, right? The x-coordinate squared plus the y-coordinate squared, square rooted, less than, or if it was equal to a number, that would be equal to the definition of a circle of radius r. So this is really just going to be a circle of radius r as the boundary, and the set that we're interested in is the inside of that circle. So that is this open ball of radius 2 centered at 0 in the usual metric for r squared. How about in the taxicab metric? Again, let's think about the points on the boundary. So we're just looking at, the sum of the differences in the x values plus the y values. So again, 0, 2 is going to be on that boundary, and similarly, 2, 0 is going to be on that boundary, and corresponding, positives and negatives. Then what else is on the boundary here for this taxicab metric? Well, one other such thing on the boundary, if both of these distances were 1, that would be right on the boundary. So the point 1, 1, and any point such that the sum of the distances was equal to 2. So that's actually going to be like a diamond shape. So that's a diamond shape filled in, and that would be this open ball for the taxicab metric on r squared. Again, the open ball centered at the origin with radius 2. So as I said, so far we've only defined open balls, not open sets. So here is the definition of an open set in a metric space. A subset U of a metric space XD is an open set with respect to the metric D if U is a union of open balls. And so that union can be finite, it can be countable, it can be uncountably infinite. It can be a union over any index set. So union alpha in whatever index sets we're talking about of open balls B, A, R over some metric D. So, and the family of open sets generated in this way is called the topology for the set X generated by D. So open sets, are going to be these open balls of whatever form they really take. It's going to be unions of things like that. And again, those unions can be finite, infinite, whatever. So something like that is kind of an abstract visualization of an open set in a topology. Here's the definition of a closed set. A subset C of a metric space XD is a closed set with respect to the metric D if its complement X without C or X minus C, or also seen X C complement, is open with respect to the metric space D, or with respect to the metric D. So a set is closed if its complement is open. That's the definition of a closed set. And a lot of people, forget this and think of it as being something else, but this is the definition of a closed set. A set is closed in a metric space if its complement is open. So here are a couple examples. So let's let XD just be a general metric space. So in that case, is the set X, the whole set X, open? Is it closed? Is it both open and closed, or is it neither open nor closed? And similarly, if we think about the empty set as a subset of any set, is the empty set open in this metric space, closed in this metric space, both, or neither? So there are definitive answers to both of these questions. I'd encourage you to really think about this in terms of that definition for open and closed sets. So do pause, think about this for a moment, and then we'll talk about it together. All right, so is the whole set open, closed, both or neither, in a metric space? Well, as we said, a set is open if it's a union of open balls in that space. And, one way we could think of X is being the union over all X in X of the open ball, X comma, take any real number that's positive, X comma 1. So if we think about that union, it's clearly a union of open balls. We have no idea, what size of kind of union this is. Like, it depends. It's just over the size of the set. So it could be finite, could be countably infinite, could be uncountably infinite, but that doesn't matter. Our definition of open is that a set is open if it's a collection, if it's a union of a collection of open balls. And this is such a set, and it is the entire set X and nothing else. So yes, because we are just inside this space, there's nothing else possible to include in it. So that tells us that X is open. All right, so before we think about whether or not X is closed, let's get something for free. We know that a set is closed if its complement is open. So what's the complement of X? The complement of X is the empty set, right? So the empty set is X minus X, or the complement of X, right? And since the whole set is open, that means that the empty set is closed. Okay, cool. Similarly, because our definition of being closed is that the complement is open, it's hard to think about whether a set is closed without thinking about its complement. So let's move on now to think again about the empty set and think about whether or not it's open. So it is also open. So the empty set we could think of as the union over nothing, the union over X in, say, the empty set of the balls of radius, again, say 1, about the point X. That is a union. It's a finite union, a union of 0 things, right? So this is basically like a vacuous union, and so that is technically a union over an index set. The index set happens to be the empty set. And because it's a union of open balls, a vacuously empty one, that means that the empty set is open. So the empty set is closed and the empty set is open. Now this also tells us that along with being open, the entire set X is also closed. Why? Because the complement of the empty set, so that's the entire set X minus the empty set, is X. And since its complement is open, that tells us that X is closed. So the complement of X is open, and therefore the entire set X is closed. So the entire set X is both open and closed in the metric space XD, which I think is pretty cool. Here's one last problem to try in this video. So let's think about whether the interval 1, 5, the open interval 1, 5 in the real numbers, is open in the following metric spaces. So let's say the usual metric on R, the usual metric on R squared, and the discrete metric on R squared. So for each of those metric spaces, is the interval from 1 to 5 open? So again, I'd like you to pause, grab paper if you haven't already, and think about each of these. Okay, so clearly this is open in the usual metric on R. 1, 5 is just one ball, one open ball, centered at 3 with radius 2. So it's the union from I equals 1 to 1 of this open ball. And so, yes, this is a union of open balls, and therefore it is open. How about the usual metric on R squared? So let's think about this. If we think about sort of just this set as a subset of R squared, from 1 to 5, this interval, and let's think about, if it is a union of open balls, then it's things of the form, ball around some point X of radius R, whatever radius, and it would be a union of things like this. So could 1, 5 be such a union? So let's take any point X. Let's take any point X in this set and any radius R. So if we take any radius R in the usual metric, that is going to contain some points where the y value is greater than 0. So if we think about any ball of radius r centered at x, then the point, let's say x comma r over 2, is going to be an element of that open ball, and therefore it cannot be the case that just that line segment is a union of these open balls, because it's going to contain things outside of this line segment. So no, this is not an open set on R squared, in R squared with the usual metric, because this cannot be a union of open balls in this metric space. So maybe surprisingly, this this interval from 1 to 5 in the set R squared actually is an open set in the discrete metric on R squared. So to see why that's true, let's just remind ourselves the discrete metric, the distance between 2 points is 0 if x is equal to y, and 1 if x is not equal to y. So, what if we thought about like an open ball around, say, the point 3, 0 of radius something positive but less than 1? What are elements of that open ball? So what can be in there? Anything of distance less than 1/2. Well, the distance is either 0 or 1. So the only things of distance less than 1/2 are the point itself. So the point 3, 0 is in that ball, and it's the only point in that ball. And so therefore, this line segment, this open line segment in the real line, actually is 1, 5 is equal to a union of balls of the form x comma 0 with radius. Again, we could use a 1/10 or 0.3 or whatever, any radius as long as it's strictly less than 1, or less than or equal to 1 even, for x in the interval from 1 to 5. That would be, again, an uncountably infinite union of points would be the elements of this union of open balls, and that is exactly this open line segment. So this is a union of open balls in this discrete metric, and therefore it is an open set in the discrete metric on R squared.